Now next we will discuss binomial distribution. It is extension of the Bernoulli distribution. So now here also we will find the homogeneity function, mean and variance. It is given x as suppose x as a binomial distribution with parameter p belongs to 0, 1. Find the homogeneity function, mean and variance of x. So how we can find that? Let us do it. So let x be a, so x be a binomial distribution, binomial distributed random variable, random variable with parameter. So binomial distribution, two parameter n and p, where n is belongs to some natural number, n can be greater than equal to 1 or 1, 2, 3 for any value, and p is a parameter 0 and 1. So the probability mass function of x is, so we know that probability mass function of x, because it is a binomial random variable, so it can be represented as p of x xk is probability that x taking some values xk, this is equal to nc xk p to the power of xk 1 minus p to the power of n minus xk, where xk can take the value 0, 1, 0, 1, 2 like this, and the 0 equal to this is otherwise. For simplicity, let us take this value, because xk, because we are taking this variable because it is a discrete only, otherwise you could take just x will be 0, 1, 2. For understanding that this is discrete random variable, that is why we are taking for some discrete values, this is the probability mass function. Now because we know the probability mass function, now we want to find the homogeneity function. So the homogeneity function of x is given by, so mxt expected values of e to the power of tx. So by definition, it takes all the possible values of xk, e to the power of txk, px of xk. This is the definition. So now in the next page we will write it. So mxt is, so e to the power of expected values of e to the power of tx. For discrete case, it is defined as k summation of k e to the power of t of xk, probability that it can be taking. So here we are taking xk. So all the possible values of xk it can take. So if xk can take the value 0 to n only. So now, so this is summation of xk can take 0 to n e to the power of txk. Then this is ncxk. This probability mass function will write this probability mass function here, it is given ncxk p to the power of xk 1 minus p to the power of n minus xk. So then just let us see that how we can simplify these things. So here you can see that p to the, so we can write like xk is equal to 0 to n. So ncxk p e to the power of t whole to the power xk 1 minus p whole to the power n minus xk. So then this has a some simplified form. So we know that it is like a binomial expansion. We know that how we can represent a plus b whole to the power n. So this is summation r is equal to 0 to n. So ncr a to the power r b to the power of n minus r. Now you compare with a is p e to the power of t and b is 1 minus of p, and then it is nothing but the xk goes to 0 to n, ncxk a to the power of xk 1 minus p whole to the power of n minus xk. So this is by a plus b, so p e to the power of t plus 1 minus p whole to the power n. So now we denote 1 minus p is q, so q plus p to the power t whole to the power n. So we denote q is equal to 1 minus p. So this is the homogeneity function of the binomial random variable. Now using this homogeneity function, we will find the moments. So similarly we will do that. It is just a practice only. Now you have understood. I think you can do also, but we just have to do the derivative. So Now first we differentiate with respect to t, mxt. So then what will be the derivative of this mxt? So this is n p q plus p e to the power t whole to the power n minus 1, and then derivative of p e to the power t will be p e to the power of t. So next, suppose if you want to differentiate again, so then d square dt square, only second order we will do it. Then again this will be n into n minus 1 q plus p e to the power of t whole to the power of n minus 2. Then the differentiation of this p e to the power of t, again p e to the power of t whole square, plus these things will be as it is, q plus p e to the power of t whole to the power n minus 1. Then we will differentiate these things, p e to the power of t, again p e to the power of t. So now we will get the mu1 dash is nothing but differentiation mxt, and at t is equal to 0, and if we put t is equal to 0, so these things we evaluate at t is equal to 0. Now t is equal to 0, this part goes to 1, this part also goes to the 1, p plus q, this will be 1, p plus q 1, because q is 1 minus p. So then this is whole to the power n minus 1 is 1, so n, so this become np. So this is n into p. So now what will be mu2 dash? Mu2 dash is second time differentiation mxt and evaluate at t is equal to 0. So then mu2 dash second time derivative at evaluate at t is equal to 0. So here if you put the t is equal to 0, so this become p square, and this is t is equal to 0, p plus square is become 1 again. So this is n into n minus 1 into p square. So this is nothing but n into n minus 1 into p square plus, so this term will be same as before. So e to the power t is 0, so this will be p, and then np, and this is t 0, p plus q whole to the power n minus, so this is 1 again. So this is nothing but np, so this is np. So then we found mu2 dash and mu1 dash, hence we can find the variance. So this is nothing but the mean expected values of x. So this is the mean, we say mean, and then the variance, how we will find the variance? So variance of x, so this is var of x we denote. So this is mu2 dash minus mu1 dash whole square. So mu2 dash is n into n minus 1 p square plus np, minus mu1 dash is nothing but mu1 dash np, so this np whole square. So now just we have to simplify these things. So this will be nothing but n square p square minus np square plus np minus n square p square. So n plus p square cancelled, np minus np square, so this is np, if you take common 1 minus p, so this is np into q, npq. So here you can see that if you can remember that how we could find the moment genetic function of we found the variance of x. It was not that much straightforward, it is little complicated from the definition of variance. If you find the second order moment, so then it was not as simple it is. So it was a complicated steps we have to find we did for finding these moments, second order moments, and then we could find this variance. But here if you know this moment genetic function, so then if you just take the differentiation rth order and take at t is equal to 0, then you get rth order moment. So here we discussed first order and second order moments, mean and variances. Now we will discuss the other examples. So what we discussed, two examples, those are discrete cases. Let us consider one continuous random variable. Find the moment genetic function mean and variance of x, where x is a normal 0 1 random variable. Let us do that. Let x is a normal 0 1. Let x as normal 0 1. Then the probability density function of x is given by probability density function of x is, because it is a continuous random variable, we will find the probability, we will use the probability density function for finding the moment genetic function. F of x is equal to 1 by root 3 pi sigma here 1 e to the power of minus x square by 2, where x is between minus infinity to plus infinity. So now for finding moment generating function, we have to find the expected values of Tx. So the moment generating function of x is given by, this is mxt, this is nothing but expected values of e to the power of Tx. So expected value e to the power of Tx. So by definition, because it is continuous random variable, it is minus infinity to plus infinity e to the power of Tx fxx dx. So this is equal to minus infinity to plus infinity e to the power of Tx 1 by root 2 pi e to the power of minus x square by 2 dx. Now we have to find what is the we have to evaluate this integration. So now how we can do that? So 1 by root 2 pi, it can be a constant. Now these things minus infinity to plus infinity e to the power of minus x square, so 1 by 2. So then this is x square minus 2 into Tx. So I want to find it as a whole square form. So up to this, it is what it is, just simply if you simplify, we will get back this form. Now we just add is the extra term, because 1 minus 2 Tx plus suppose t square and also subtract t square, then dx. So this so these things, so this is 1 by root 2 pi minus infinity to plus infinity e to the power of minus 1 by 2 x square minus 2 Tx plus t square can be written as x minus t whole square into this minus and plus e to the power of t square by 2 and then dx. So this is a constant. So this is e to the power of t square by 2. So minus infinity to plus infinity 1 by root 2 pi e to the power of minus x minus t whole square by 2 dx. Now what will be the value of this function integration? So note that if you have a suppose instead of normal 0 1, suppose if you have normal t is any real number, so t 1, so then what will be the density function? So this density function of fxx will be 1 by root 2 pi e to the power of minus x minus t, this is the mean mu whole square by 2. So because if x is a normal t1 and if this is a density function, then this integration minus infinity to plus infinity, because it is a density function of a normal distribution, this density function will be integration minus infinity to plus infinity, integration will be is equal to 1. So here you can see that this is exactly the same density function it is. So that's why this will be is equal to 1. So finally what we got using this property, because this is we have already shown whenever we discuss the normal distribution for a any mean mu and variance sigma, whenever you use a density function, then this integration will be is equal to 1, that we have already shown. So here we will not again compute this integral. Instead of that, we will use this property, that density function, property of a density function, and that's why we use that this is equal to 1. So we simplified this. This is the moment generating function of a standard normal random variable. Now we have to find the mean and variance of this random variable. So you can remember that whenever we discuss this normal distribution, mean and variance computation was little tricky. Now what we will do, we know that this moment generating function is, so if now we know that x is normal 0 1, then moment generating function is mxt is nothing but e to the power of t square by 2. So moment generating function is e to the power of t square by 2. So then how we will find the let us do the differentiation with respect to t. So this is ddt of mxt. So this is e to the power of t square by 2. So this is e to the power of t square by 2, and then t square by 2 2t by 2. So then this cancels. So t e to the power of t square by 2. Now next, if we do again differentiation with respect to t, so then this is e to the power of t square by 2 plus plus t into again the same thing e to the power of t square by 2 into 2t by 2. So then this is simplified form is e to the power of t square by 2 plus so this will be, if we take the common e to the power of t square by 2, then 1 plus t square. So this is coming the second order moment. So the second derivative actually. So then from here we can find, which implies the first order moment expected values of x. So from here, so mean is equal to expected values of x this is nothing but mu1 dash. So if you, how we can find that? So we will do the derivative with respect to t and evaluate at t is equal to 0. So these things we evaluate t is equal to 0. For now t is equal to 0, if you put, this is nothing but 0. So this is the mean of a standard normal variate, which is 0. And what is the second order raw moment? So mu2 dash. So mu2 dash is expected value of x square. How we can find that? So this is the second order moment, second time derivative, whatever we found, we evaluate t is equal to 0. So here second order, so t equal to 0, this is 1, and t square is 0, so 1. So this is becoming nothing but 1. So then variance will be variance of x. This is nothing but, so we denote sigma square. So x, this is mu2 dash minus mu1 dash whole square. Mu1 dash is 0, so this is nothing but mu1 dash, this is 1. So 1 is the variance here and 0 is the mean. So that we just very simple, just define, we know the moment generating function, then very it is very simple to compute the mean and variance of this random variable. Now this was the one of the example. So next we will discuss some other properties of the moment generating function. So let us discuss this property. Let x be a random variable with moment generating function mxt, and find the moment generating function of y. So it is a transformation of random variable ax plus b. So let us find this. So let x be a random variable with the moment generating function mxt. So this is general function. So some of the particular random variables, suppose it is normal 0 1, then it will be e to the power of minus t square by 2. But in a general, we writing mxt and y is equal to, so y it is given as ax plus b. So y is equal to ax plus b for some a and b, two real number. So a cannot be if a is 0, then this will be just a constant, and b is a any real number. So a also any real number not equal to 0. Now how we can find the moment generating function of y? So in term of mxt. So moment generating function of x. The moment generating function so usually we abbreviate. So let us write this moment generating function mgf of y is given by m of yt. So by definition e to the power of 2ay. By decimation myt is nothing but expected values of e to the power of ty. So now y is, so expected values of e to the power of t into y is ax plus b. So this is expected values of e to the power of tax plus e to the power of, sorry, it is multiplication into e to the power of tb. So e to the power of t, b is a real number, t is a real number, so it will be outside e to the power of tb. And now expected values of e to the power of tax. Now what is mxt? So since mxt is the, since mxt is the moment generating function of x, so mxt is nothing but expected values of e to the power of tx. So we assume that this moment generating function exists for some values of t. So mxt, this function of t, it is nothing but expected value of tx. So hence e to the power of ta into x, ta is a real number, so this is nothing but e to the power of tb. So this is mx of ta, because mx of, if you replace this t by ta, e to the power of tax. So that is the things we have written as, so mx of ta. So now using this concept, so this is in general case. So if you know the moment generating function of x, then we can replace here t by ta, then we can find this function, then we can directly find the moment generating function of y also. So here you can see some next example. Suppose x is normal mu sigma square. Using the above two results, like you know the moment function of x, and in this transformation above two results you find the moment function of x is normal mu sigma square. So now suppose x is normal mu sigma square. Now if you take this transformation, y is equal to mu plus sigma x, where okay, so x is here, so let us take z equal to these things. So just because x is it is given here, so x this notation normal mu sigma square, or you can take, let us consider instead of this y, and x you take normal 0 1. Then if you consider y is equal to mu plus sigma x, then we want to find the homogeneity function of y. But what is this distribution? So earlier we discussed that uh, any linear combination of a normal distribution, whenever we discussed in the normal distribution part, it is again a normal distribution. So now it will be a normal distribution, some mean mu and variance sigma square, because if you can, we know that this is a normal distribution, just we have to find the mean and variance. So if you find the mean expected values of y, so this is nothing but expected values of mu plus sigma x, this is mu is a constant plus sigma into expected values of x. Now expected values of x is 0, so x is normal 0 1, which implies expected values of x is 0 and variance of x, this will be equal to 1. So this, see, in that case this is nothing but expected value of x is 0, so this is mu. Now what will be the variance of y? Variance of y will be variance of mu plus sigma y. Now variance of sigma, it is a constant, so this property also we discussed. If you add the constant to a random variable, variance does not change, variance of sigma y. So then sigma is a constant, it will be another property we discussed earlier, the sigma square it will be outside into variance of y. Sorry, this is mu plus sigma x, it is sigma x, then sigma x. So this is variance of x, sigma square into variance of x. Now variance of x is 1, so this is become sigma square. Hence y, if you take y is equal to mu plus sigma x, it will be nothing but normal distribution with mean mu and variance sigma square. So using these properties, this transformation we have computed. Suppose we know the probabilities of standard normal variate, the table we can use and we can find the probability of y. So y is any normal distribution using this transformation that we discussed in the earlier some of the lectures. You can see that we discussed those problems. Now we want to find the homogeneity function of y, where y is normal mu sigma square. Now we know the homogeneity function of x, and also we know this property. So here we will use this property. So this property says that the homogeneity function of y is given by m of yt. So now you can see that, so ax plus b, so what is a here? So ax sigma is a here, so this is e to the power of t into b into mx of ta. So now what is b? So b is a constant, that is mu here. So this is e to the power of t mu into mx of t into sigma, t is, so sigma x, so mu plus sigma x. If you relate with these things, this result, and here actually we have sigma x, mu plus sigma x. So in this case, so here in this transformation, so then if you relate, this mu is nothing but b, so that's why it is about t mu, and sigma is nothing but x, so that's why t of sigma. So then what we found, that the homogeneity function, hence the moment generating function of y is m of yt. So this is nothing but e to the power of t mu into mx of t sigma, mx of t sigma, where x has normal 0 1 and mx t is expected values of e to the power of tx. So this we know, this is nothing but, here we computed for normal 0 1 mxt is e to the power of t square by 2. So hence what we found, this is e to the power of, we know that this value is expected value of e to the power of t square by 2. Hence mx of t sigma, it will be e to the power of t square sigma square, we replace t by t sigma, t square sigma square by 2. So that we will replace here e to the power of t mu into e to the power of t square sigma square by 2. Hence this is nothing but t mu plus t square sigma square by 2. So this is the homogeneity function of a. Hence we found that if y is normal mu sigma square, then myt is nothing but expect e to the power of t mu plus t square sigma square by 2. So this is the homogeneity function of a normal distribution with mean mu and variance sigma square. So in the particular, if mean mu is 0 and sigma square is 1, you can see that it is nothing but e to the power of t square by 2, that is the standard normal homogeneity function of a standard normal random variable, but it is the more general case. But we did not do this complicated integration, just using these two properties we found this. So that's why it is saying that find the homogeneity function of x using the above two results. So that we completed here. Hopefully you are following or you are understanding it. You do more like you can find the homogeneity function of Poisson distribution, other random variable uniform distributions, exponential distribution, gamma distribution, and then moments also you can find, you can practice those things. So then it will be more clear to you. So some important theorems now we will learn. If two random variables have the same homogeneity function, then they must have the same distribution. So that is one of the very important theorems. We are not going to prove this theorem, but it has important, very significant applications and implications, because if homogeneity function exists, so it cannot be 2, 3 different homogeneity functions. So that means if you know the homogeneity function, by homogeneity function also you can identify the random variable. So it is a Poisson, or it is a normal distribution, or it is a exponential distribution. If you know the homogeneity function, so if you can find the, suppose one unknown random variable, you are taking a transformation of random variable, we don't know the distribution. But if you can compute the homogeneity function, and if you see that this homogeneity function looks like very similar to some of the known homogeneity function, like it is looks like a Poisson distribution homogeneity function, then it will be a Poisson distribution. It cannot be other any distribution. That's why if two random variables have the same homogeneity function, then they must have the same distribution. They cannot be different. So that's why by homogeneity function also we can identify the distribution. So here some of the application will do. So here let us do this this example. Let x1, x2, xn be independent distributed random variables with homogeneity function of xi being mxti. Then let us first find the homogeneity function of the sum of the random variable. So they are independently distributed random variable. So let us do that. So here this is the uniqueness. First of all, let us write this unique theorem to so that we can utilize it, use it in the following problems. Let x and y be two random variables with homogeneity functions mxt and myt respectively, satisfying such that mxt is equal to myt for all t. So if it exists with some interval, then it will be equal to in the same interval. Otherwise, if it exists for all real number, it is same. So basically this homogeneity function is same for all t where it is defined. Then the fxt, fx of x should be is equal to same as fy of x for all x belongs to the real number, where x and so where fx x and fy y, where fx x, so you can write it is a, because it is a variable, fx dot is the CDF of x and Fy is the cumulative distribution function of y. So that means they have same distribution function. Same distribution function means, so if we consider the probability mass function, that means if they are discrete then they have same probability mass function. If they are continuous then they are same probability density function. So these two random variables are basically same random variables. So that is the uniqueness.